Rather strangely, I stumbled across a quadratic equation for the first time in many, many years whilst I was thinking about an optical illusion. Now, if you search online, you will find thousands, actually probably millions of different optical illusions. But by far and away, my favorite is the one here, because although it looks innocuous, it is absolutely mind-bending. If you haven't seen it before, the squares marked A and B are actually the same color. Now, however long you look at it, from whatever angle, you will never see them as the same color, but trust me, they are. In fact, really the only way to prove it to yourself is to print out two copies of the image, cut out the square marked A from one of them, and then physically slide it between the two squares in the other copy of the image. However, as most people are probably not going to do that, I wanted to create an interactive version of this for people to play with online, and this is what I came up with. It allows you to use the slider on the left to move the square from A to B and back again. Unfortunately, this just looks like the square is changing color as it moves. So I thought maybe if I made the tile a dot instead, it would help, but that doesn't seem to. So finally, and this is where the quadratics come in, I thought it might help if the movement was curved rather than straight. So I added a curve factor, but in fact, this just further accentuates the illusion as it looks even more like the dot is changing color as it moves. So if you want to prove this is an illusion, and I'm not cheating by changing the color of the tile or the dot as it moves, then you need to get your scissors out. But that's not the point of this video. What I want to do here is to explain where quadratics come in. To do all of this, I used a spreadsheet tool called Squirrel 365, which amongst many other things allows you to move things around based on spreadsheet logic. So what we have here are two images. Image 1 is the chessboard, image 2 is the tile we want to move from down here to up here based on a slider. So if we add the slider to the canvas, change its orientation to be vertical, make it a percentage from 1 to 100, and then bind it into this yellow cell here. So when we run the project, the slider moves the value in that cell up and down between 1 and 0, just like a normal spreadsheet percentage. So what we want to do with that percentage is calculate intermediate values between the start and the end for the x and y positions. So at the start, the xy position is 531, 348. So we type those in. Then we move to the end position, get the values 542, 222. And then we're going to calculate the intermediate. And the intermediate is just equals the start position plus the end position minus the start position times the percentage that we've traveled. And make those into absolute values so they'll copy down nicely, and then copy that value into the cell below. Now all that remains is to bind those intermediate xy values to the tile. So we bind the x and bind the y, and hey presto, based on the changing values in the spreadsheet, the tile moves up and down with the slider. It was at this point that I thought it might be better for the tile to move in a curve like this rather than straight up and down. So I needed to add something extra to the formula for the horizontal position that would leave it the same when the slider was at 1 and 0, but move smoothly away and back again from the current path in between, which took me back to a shape like this. It has a value of 0 at 0 and 1 and moves smoothly away and back again in between. I needed an expression for this curve, which is a parabola, and it's defined by a quadratic. The general expression for a quadratic is ax squared plus bx plus c, so I needed to find a, b, and c. But then the whole concept of factorization came flooding back to me, and I realized I could also write this as x minus r1 times x minus r2, where r1 and r2 are the points where the curve crosses the x-axis, which we know are 1 and 0. So plugging those in gives x minus 0 times x minus 1, which simplifies to x times x minus 1, which is the expression I need. Well, almost. The only issue is that the maximum movement away from 0 that this would give is this distance here when x is 0.5. And plugging that into the formula gives 0.5 times 0.5 minus 1, which is 0.5 times 0.5, which is 0.25, which is a quarter. Now, a quarter of a pixel of movement, which is not really enough to make the point. Something more like a movement of 200 pixels would be better, which is achieved by multiplying the whole thing by 800. So my final expression is x times x minus 1 times 800. So back in Squirrel, we just need to add that little quadratic on the end of the x position, which is plus the percentage moved times the percentage moved minus 1 all times 800. If we run the project, the tile moves a nice smooth arc between the top and the bottom positions. And that is how I stumbled across a quadratic.